Okay, in this discussion I want to introduce variational methods and first talk a little bit about why we do it, why it's important, why it's useful in analyzing materials and fields within materials. So first let's note that it's a compact way of describing material behavior in terms of changes in energy. So what I mean by that is we'll often pose problems in terms of its energy and then apply some boundary conditions and see how does that energy change, what are the underlying influences on the governing equations. So by doing that we can assess or analyze reversible behavior and compare this with dissipated effects. So if you have a material that goes through phase transformation, if it undergoes plasticity, fracture, we can start identifying where are those dissipative mechanisms occurring and how does it contribute in the grander scheme of the reversible behavior. So you can also test different kinds of hypotheses. So often we can't solve everything ab initio from quantum mechanics, so we have to make some approximations on material behavior, such as is it linear elastic behavior? So stress times my strain gives me a measure of internal energy. We can write that stress, if it's a simple 1D model, in terms of a modulus and strain. So we can compare this to measurements and see how well does it describe what we see in the laboratory. And then understand what's our modulus, is it really linear, is that a good enough approximation for what we're trying to understand. One of the other key things to note is due to first law of thermodynamics, energy is always conserved. So we're going to be using a few different forms in the class, particularly looking at stored energy, different types of stored energy, whether it's elastic, mechanical energy, whether it's different types of electromagnetic, maybe dielectric energy in a capacitor, maybe magnetic energy in some type of magnet. In other cases, we're dealing with dynamics, so we have kinetic energy, and particularly what I'll focus on here is what's known as Lagrangian density. So that's taking that kinetic energy minus the stored energy, and we use that as another form of the combined energy. You may also see Hamiltonian used. Either way, you will lead to a set of balance equations that are self-consistent and can be used to study materials. Alright, next thing important in this page is this action integral, which describes the integration of this Lagrangian. And remember, my stored energy, my kinetic energy, they're in terms of an energy per volume. So that's why we call it density. So here I'm integrating that density over the whole volume of our material, omega, and I'm integrating it over some time from T1 to T2. So I call this an action integral. And the way I'm going to set up a set of equations that we can solve either by hand or by computer is I'm going to take what's called a variation on that action integral. Since the energy is conserved, regardless of its reversible or dissipative, we can't create or destroy energy. So this has to be constant. Okay, so there's no variation in that action integral. Now you have to be very careful with your control volume. So if there's fluxes of energy coming in and out, we have to include that as part of the action integral. Okay, clearly the energy will change inside here if you have more coming in than going out. We count these fluxes on the surface as part of that energy, and in that case this will be 0. So this we'll be using quite a bit. It's a variation operator. We'll apply it in mechanics. We'll also apply it in electromagnetics. In mechanics, you'll often see this called principle of virtual work.